Good evening, and welcome to the Obscura Institute. The lamps are lit, the archive is open, and tonight we draw a single file down from the shelves. File 11. The interstellar visitor called Oumuamua. Settle in, make yourself comfortable, and let us begin. On the night of the 19th of October 2017, a telescope on the summit of Haleakala on Maui was doing what it does most clear nights, sweeping the sky, taking images, comparing them against the images from the night before, looking for anything that has moved. A postdoctoral researcher at the University of Hawaii's Institute for Astronomy, a Canadian named Robert Werrick, was going through the results. The telescope was Pan-STARRS 1, built largely to find asteroids that might one day come uncomfortably close to Earth. On this particular night, it had picked up a faint smudge of light that didn't match anything in the catalogues. Werrick went back to the previous night's image and found it there too, shifted well across the sky, about 12 times the width of the full moon in a single day, and nothing in the ordinary inventory of the solar system moves like that unless it is very close and moving very fast. The speed was interesting on its own, but it was the shape of the path that would matter. Everything gravitationally bound to the Sun travels a closed loop. A planet, an asteroid, a long-period comet that takes 10,000 years to come round. They all follow curves that eventually bring them back. Astronomers describe how stretched a given orbit is with a number, and once that number passes a certain threshold, the curve stops closing altogether, becoming an open path, in, around, and out, never to return. Oumuamua's number was not marginally over the line, but well past it, and there was no orbit to refine, no earlier appearance to dig out of the archives, because this object had come in from interstellar space, whipped around the Sun, and was already on its way back out. The speed it keeps, once the Sun has finished pulling on it, is about 26 kilometers a second. That is the speed it will carry into the dark, more or less forever. It had been closest to the Sun on the 9th of September, roughly 40 days before anyone noticed it, passing well inside the orbit of Mercury, and its closest approach to Earth came on the 14th of October, at about 60 times the distance to the Moon, close in the scheme of things, and utterly unremarked at the time. It came in from the direction of Lyra, a small constellation with one very bright star in it. That star, Vega, was somewhere else entirely when Oumuamua passed through. Stars drift over the time this thing had been traveling. The incoming direction happens to lie near the direction our own Sun is traveling through the galaxy, so that an object drifting more or less at rest relative to the local swarm of stars would appear to come at us from about there, the way rain on a still day appears to fall towards a moving windscreen. The naming committees had no category for it, so they made one. The designation is 1I 2017 U1, the I standing for interstellar, a class of object that had been theorized for decades and had, until that October, never once been caught. Astronomers around the world turned whatever they could towards it. It was very faint, and it was getting fainter every night as it pulled away, so the useful work happened fast. There is no photograph of Oumuamua, and there never will be. Even in the largest telescopes, it was a point of light, indistinguishable from a star apart from its motion, and everything we think we know about its form was worked out from a single measurement, repeated over and over, how bright that point was, minute by minute. That is a genuinely powerful technique. If an object is spinning and it isn't a sphere, it turns a wider face towards you and then a narrower one, and its brightness rises and falls in step, and the size of that swing tells you how lopsided it is. A team measured the swing, and it was extraordinary. The object at its brightest was about 10 times brighter than at its dimmest, which taken at face value implies something roughly 10 times longer than it is wide. And nothing in the solar system is shaped like that. Not asteroids, not comet nuclei, not anything on file. That single measurement is the origin of the picture almost everyone has seen. The dark, reddish splinter tumbling against the stars, like a shard of rock chipped off something larger. That image is an artist's impression, drawn from the light curve rather than from an observation, and it has done more to shape public understanding of Oumuamua than any paper. Later, analyses softened it, bringing the ratio down to something more like 5 or 6 to 1. Still unusual, still nothing quite like it on file, but less extreme. And the light curve doesn't uniquely demand a long, thin splinter at all. A flattened disk, a kind of pancake tumbling as it goes, fits the same measurements as well or better, and some analyses prefer it. The object was either a splinter or a wafer, and we don't know which. The rotation had its own complication. Estimates cluster somewhere between about 7 and 8 hours, but Oumuamua wasn't spinning tidally around one axis. It was tumbling, turning chaotically, the way a badly thrown object turns, which means no single rotation period is exactly right. Color we could get. It was red, comparable to the darker asteroids of the outer solar system and to the icy bodies of the Kuiper belt beyond Neptune. And that reddening is the expected signature of a surface left out in space for a very long time, slowly cooked by cosmic radiation. How much light it reflected was never pinned down. The estimates ran from something like 1/10 up to rather more, and the difference was never settled. Size follows from brightness and reflectivity, and since reflectivity was uncertain, so was size. The plausible range ran from something around 100 meters long to perhaps a kilometer. The name came from Hawaii, where it was found. Astronomers consulted Hawaiian language experts at the University of Hawaii at Hilo, Kayu Kimura and Larry Kimura, who offered Oumuamua. It means something like a scout or a messenger from afar, one who reaches out first, and it begins with a catch in the throat before the vowel, a small held breath at the front of the word. It's a good name, chosen with care. It does not, of course, imply anyone sent it. Through late October and into November, observations continued as the object dimmed. Then, in June 2018, a paper appeared in Nature that changed the character of the whole story. A team had been fitting the observations to a trajectory the path gravity alone would produce, accounting for the sun and the planets, and the fit was slightly wrong, not by much, but consistently and in a specific direction. Oumuamua was being pushed away from the sun by something in excess of gravity. The push weakened with distance from the sun, though the data were too sparse to say exactly how steeply, and the total effect on the object's speed was modest, not a lurch of any kind, but a nudge, sustained over weeks. In itself, that finding should have been dull, because comets do this constantly. As a comet nears the sun, its ices turn to gas, the gas jets off the sunlit side, and the comet is pushed the other way. Astronomers have modeled that effect for decades, and there is nothing surprising in it. The trouble was that Oumuamua showed none of the accompanying evidence. There was no coma, the fuzzy envelope of gas and dust that gives comets their soft look, and no tail. Deep images taken specifically to look for one turned up nothing, and spectroscopy found no emission lines from escaping gas. In November 2017, the Spitzer Space Telescope stared at where Oumuamua should be for just over 30 hours in the infrared and failed to detect it at all. That non-detection was useful. It set hard ceilings on what could be coming off the surface and tight limits in particular on carbon dioxide and carbon monoxide, which are the usual suspects for driving activity in a cold, distant comet. The Spitzer limits effectively removed them from consideration. And the numbers don't merely fail to match, they conflict. To produce the observed push, far more gas would have to be leaving than the dust searches allowed. A comet cleaner than any we have ever measured. There is one further caution. In 2019, a researcher who reworked the data argued that the acceleration signal itself may not be as robust as claimed, that the object was faint, the observations sparse, and the small mismatch in the fit might not carry the weight placed on it. It is a minority position, and most of the field accepts the detection, but the entire mystery rests on that one measurement, and not everyone was convinced by it. People tried, in turn, to imagine what could push without a tail. The first idea was a shard of nitrogen ice. On Pluto, nitrogen ice covers large regions of the surface, so if something struck a Pluto-like world in a distant planetary system and blasted fragments free, one of those fragments might drift for a very long time before arriving here. Nitrogen ice turns to gas readily in sunlight, so it would push, and it is nearly transparent, bright, and produces almost no dust, a push you could not see. But other astronomers found it hard to see how such a thing would survive the heat, and harder still to account for the sheer number of shattered Pluto-like worlds you would need out there for one splinter to cross our path in the few years we've been able to look. The next idea went the other way. Instead of something that evaporates, something so light that plain sunlight could move it. Picture a fluffy, hyperporous clump of dust, a fractal thing mostly made of empty space, so airy it was mostly nothing at all. Sunlight carries momentum, feeble momentum, but if an object presents a large area and almost no mass, that pressure is enough to push it, and it would weaken with distance exactly as observed, with no outgassing needed, and so no tail to see. The difficulty is survival, something that flimsy would have to hold together through the strain of a close pass by the sun, and it is easy to build such a thing on paper, and rather harder to keep it intact through a run inside Mercury's orbit. Which brings us to what is currently the strongest answer, published in Nature in March 2023 by Jennifer Bergner and Daryl Seligman, and it begins with ordinary water ice. Out in interstellar space, over millions of years in the dark and the cold, cosmic rays bombard that ice and split water molecules apart, and some of the fragments recombine as molecular hydrogen, which gets caught in small pockets in the ice structure rather than escaping until the ice has become a quiet reservoir of stored hydrogen. Bring it near a star, and the ice warms and reorganizes, shifting from a disordered state to a crystalline one, and that rearrangement releases the trapped hydrogen, which streams off the sunlit side. The elegance of it is that hydrogen is invisible to the searches that were run. It produces no coma anyone could photograph and no emission lines in the observed range. Spitzer was looking for carbon monoxide and carbon dioxide, and there wouldn't have been any. Meanwhile, the object is small enough that a modest hydrogen flow gives exactly the observed nudge. It requires no new physics and no exotic population of parent bodies. It says Oumuamua was a fairly ordinary lump of water ice that had spent a very long time somewhere very cold and very irradiated, which is precisely what you'd expect of anything that has crossed between stars. It isn't confirmed, and it can't be, because the object is gone. But of all the explanations, it is the one that strains the least. In November 2018, some months after the acceleration paper, a study appeared in the astrophysical journal Letters by Shmuel Bialy and Avi Loeb, a respected astronomer who was at the time the chair of Harvard's astronomy department. Their argument was structured as physics rather than as a claim about aliens. If the push weakened with distance in the way sunlight does, then perhaps sunlight was doing it. And for sunlight alone to produce a push that size, the object would have to be extraordinarily light for its area. A sheet well under a millimeter thick, spread across tens of meters. There is a name for an object with that geometry, and it isn't a natural one. It's a light sail, a technology humans have already tested in a small way. A large reflective sheet driven by starlight or by a laser. Byerly and Loeb suggested Oumuamua might be one, possibly defunct and adrift, possibly a probe, and Loeb went on to argue the case at length, including in a 2021 book, Extraterrestrial. Most of the field thought the assumption was doing all the work. There was no independent evidence for the required thinness. It came out of assuming sunlight was the cause and solving for what shape would fit. The tumbling, in particular, sat badly with a sail, which would want to hold its face to the light, and Oumuamua was turning end over end. The reddened, weathered surface looked like natural material, and there was no signal. A listening project pointed a large radio telescope at it and heard nothing across the frequencies it searched. In 2019, a panel of specialists convened at the International Space Science Institute in Bern published an assessment in Nature Astronomy under the title The Natural History of Oumuamua, and their conclusion was that a natural origin accounts for the observations, that nothing they could see required anything made. Whatever one makes of the proposal, the episode is a fair illustration of how thin the data really was. A handful of nights of photometry and a small residual in a trajectory left room for a professional disagreement this wide. Which brings us to the thing that governs everything else: the timing. Oumuamua was found on the way out. It had already rounded the sun 40 days earlier and was accelerating away when the first image was taken, so that every night after discovery it was further and dimmer, and the window was closing before it opened. The intense ground-based campaign, the nights that produced the light curve, the colors, the spectra, ran roughly 11 days from late October into early November 2017, though faint follow-up continued afterwards, including with Hubble, into January 2018, and it was those later measurements that made the acceleration detection possible. About 11 days of good observations then, spread across a longer, thin tail of tracking. Either way, it is almost nothing. Consider what we routinely do with a solar system comet. Watch it for months, track it across successive returns, occasionally send a spacecraft. Against that, Oumuamua gave us a bare week and a half of decent data on the most consequential object of its kind ever seen. And what was missing was precisely what would have settled things. There was no resolved image, so the shape remains a deduction from a wobbling brightness. No reading of composition at the level that would name its ices, no mass, and so no density, and so no way to distinguish a solid shard from a fluffy aggregate from a thin sheet. Every one of the competing explanations turns on numbers we never obtained. On the 30th of August 2019, a Russian amateur astronomer named Gennady Borisov, observing with a telescope he had built himself, found a comet on another unbound path. It became 2I Borisov, the second interstellar object. This one arrived under better circumstances, caught about 3 months before its closest approach to the Sun, so that instead of a week and a half of a fading dot, astronomers had months on an object that was still approaching and brightening. And it looked entirely normal: a coma, a tail, ices boiling off in sunlight, behaving exactly as comet ices do. Its composition was somewhat distinctive, unusually rich in carbon monoxide compared with most solar system comets, which tells us something interesting about the cold place it formed. But nothing about it was mystifying. It was a comet from elsewhere, and it acted like a comet. That comparison cuts in an awkward direction, because it means the strangeness of Oumuamua isn't a property of coming from another star. Interstellar objects can be perfectly ordinary. Whatever made the first one odd was specific to it, or specific to the fact that we caught it late, poorly, and on its way out. In 2025, A third came, 3I Atlas. The work on it is still developing, but early analysis suggests a very old origin, possibly associated with the population of stars considerably older than the Sun. What that means will take time to settle. 3 in 8 years, after none in all of history, is not coincidence, but capability. We only started finding these things when survey telescopes became good enough to notice a faint, fast dot and flag it the same night. That capability is about to improve sharply. The Vera C. Rubin Observatory in Chile is beginning a 10-year survey of the southern sky, repeatedly imaging the whole visible sky, built precisely to catch things that move and change. Estimates for how many interstellar objects it will find vary widely because we still have only 3 data points from which to guess at the population, but the direction is clear. These objects are not rare. They were only ever invisible. And there is a plan for what to do when one appears. The European Space Agency's Comet interceptor, with launch planned around 2029, is designed to be parked in space, waiting without a target until something suitable is found, and then to go. The first mission built to chase an object that hasn't been discovered yet. If it works, someone will get close-up images of a body formed around another star, and its shape will be a measurement rather than an inference, its composition data rather than an upper limit. Oumuamua will not be that object. It is out past the outer planets now, in the cold and the quiet, still carrying the same 26 kilometers a second it arrived with, heading in the general direction of Pegasus, drifting further from the Sun every hour without any of the fuss it caused down here. No telescope will recover it. It will not come back, and it will keep going long after everyone who argued about it is gone, out through the dark between the stars at the speed it has always had, on and on, for a very long time. Which explanation sits easier with you? A strange, half-frozen shard of another star system, or something that was actually built? Tell us below before the light goes. And that is where we leave File 11 for tonight. Thank you for spending this quiet hour in the archive. If you enjoyed this case file, a like and a subscribe genuinely help the Institute grow, and turning on notifications means the next file finds you the moment it opens. The lamps will stay lit, and the Institute will be here whenever you wish to return. Until then, rest well.